Let's now put together some of the concepts we've learned to understand the phenomenon of the spruce budworm outbreak. So the spruce budworm is a pest that lives in trees and eats the leaves. And if that's all there was, then what happens is that the spruce budworms, they reproduce, they compete for the resources of the trees that produce enough leaves to support a steady state population of budworm. However, in addition to that, there are birds that like to eat the budworms. When there's not very many budworms, then there's not very many birds because there's not much food to eat. But when the budworm proliferates, then the birds start eating them voraciously. And at some point, when there's lots of budworms, the birds are eating them as fast as they possibly can. And there is then two basic states of the system. One, when there's so many budworms that the birds can't eat them fast enough, and this is what's called the spruce budworm outbreak. And then another situation where the birds essentially control the population of the budworms so that there's not very many of them altogether. And so to understand this phenomenon between a small population of budworm and a large population happening suddenly, let's try and write down a very simple dynamical equation that accounts for the various factors that determine the population of budworms. So let's call n the number of budworms, and let's write an equation for the time rate of change of the number of budworms. And there'll be two terms that describe this. There's a general growth term, and there is a loss of budworms due to predation. And for the growth term, I'll just take simple logistic growth. That is that the spruce budworms reproduce at a rate r, and so there would be exponential growth. But then there is competition for resources because they start outstripping the resources. And so there's a logistic term where the carrying capacity K tells me what is the steady state population of budworm that's limited by how much leaves the trees produce. But then now let's include the effect of predation by birds. And the idea here is that when there's not very many budworms, then the birds don't eat very much because there's not very many worms to eat. But when there's lots of budworms, then lots of birds appear, and they're basically eating as fast as they can. But at some point, a bird can't eat faster than, say, one worm per second. And so the predation rate will saturate if the number of budworms exceeds a certain value. So to try and capture that phenomenon, let's write the following: n squared 1 plus n squared, which captures the feature that for small n, the predation rate is increasing with n, and for large n, the predation rate is saturated at some value. And what we want to do now is try and understand the types of fixed points and the dynamics of the system as a function of our control parameters, which in this case are r and k. Notice that I've chosen parameters and normalized things in such a way that there's only two parameters in the system. In general, when one is dealing with nonlinear equation with many parameters, it's always useful to rescale the time, to rescale the densities, to try and minimize the number of parameters. And in this way, one gets a general understanding of the system without carrying lots of parameters. So our goal is to try and understand the dynamics, and the first step is to determine the fixed points of the system. And it turns out there's two types of fixed points. There's one fixed point which is trivial, which is just n is equal to 0. You can see that since everything is proportional to n, if n is equal to 0, then that's one fixed point. There is then a non-trivial fixed point, which is determined by the competition setting these two terms equal to each other. And so the second fixed point is determined by the condition that r, 1 minus n over k, is equal to n, 1 plus n squared. So in order to determine the dynamics of the system, we're going to have to understand where is this fixed point, what is the stability of this fixed point.